Draw the free body diagram of the right side with the break right there. Draw a free body diagram of the right side with the break right there. What would it look like?
On the right side, you said?
Yeah, right. Okay, now I want you to draw a free body diagram of the top part. See, everybody look up here for a minute. Look at where I'm breaking it. I'm breaking it here, here, and here. So we're only drawing this part right here. Draw a free body diagram of that. Yeah. Yeah, well, let's go over this right now. Okay, so I asked you to draw a free body diagram of the right side, cutting it where the red line is, right? So we're really just drawing a free body diagram of point E. What do I have on point E? I have 1,000 pounds, and, sorry, I need to look. I have ED and EF. And what is this? Is it 6 horizontal, right? Right? And then what if I draw a free body diagram of the top part of my curve? That would be joint D, right? And at D I have 2,000. And then what?
DF goes straight down.
Okay, DF going straight, thanks. DF going straight down, what else?
CD
CD, X,
CD to the left,
okay,
D to the right.
down,
To the right.
oh,
No,
just
it's horizontal.
sorry. And what is this, D what?
D.
I'll call it ED. Start with the origin and the other.
Yeah.
Okay,
Wait, does the normal go in there? Since the normal goes, like, it would go all the way through?
no, the normal would only be exerted on this joint right here.
Doesn't, like, go
No,
all the way-
because, a good question. On D, do I put the normal? No, because the normal is impacting this point, which is impacting this, this, and this. So the normal is transmitted through here, and it goes up here. So when I include DF in it, I'm already including part of the normal. So you only look at that, what's on that joint, and the only thing on that joint is the 2,000 and then these 3 guys coming together.
On your left free body diagram, you just have it labeled as ED,
Okay?
just labeling wise, and then on the other one it's DE.
Yeah, that's fine. So you could just, do this, say ED is equal to DE,
Okay.
somewhere on here. Or you could just call it, probably would be better to call it ED.
The same thing. Okay,
Yeah, just
that's
call
all
it
I
the
was
same
thinking.
thing, yeah. So, what we're doing right now where we're drawing a free body diagram, these are called joints. So for vocabulary, what is this beam called? A member. These things are called members of a truss. Members. What are these called? Joints. So what happened is when I broke it with the red line and I wanted to just do the right side, I really am doing a free body diagram of joint E. And here I'm doing a free body diagram of joint D. Okay? It's the same as separating it at the green, right? You're just seeing more of the truss. Then here you're just really seeing one joint. Don't these free body diagrams bring you back to like the first day of class? Because what are we looking at? Three forces that are concurrent. They're all acting on the same point. So what equations do I have? Some of the forces in the x equals 0. Some of the forces in the y equals 0. Do I have some of the moments? No. So how many unknowns could I have at most in here? 2. Sure enough, I have an ED and an EF. How about, let's look at D. How many unknowns do I have here? I have 3 unknowns. Can I solve these 3 in this free body diagram? Can I solve any of them?
Yeah.
Which one?
Yeah.
I do sum of the forces in the y equals minus 2,000 minus df equals 0. df is equal to minus 2,000 pounds. And that means df is in compression or tension? Compression. So that one I can solve, but I can't get these guys. But what do I know about these guys? They're equal to each other because they're both sum of the forces in the x and they're both in x. But if I do joint E first, and then I find ED, then can I go here? Yeah, because then CD is equal to ED. So this, the analysis on trusses where you're only analyzing joints is called the method of joints. When you break a truss at some point, it's called method of sections. But they're really the same. It's all really method of sections, right? I'm just sectioning it off right here. I'm sectioning it off right here. So method of joints is kind of like method of sections. It's the same kind of thing. But how many equations do I have? Can I use for each joint? 2. With a section, I could use 3 equations. See, you know how to do this already. So it's a statics problem. You got to start from the beginning, right? First thing you do is given, find, right? The table. I would say we probably wouldn't do tables with trusses anymore because there are 13 members here, plus 2 here and 1 here. That's 15 unknowns. But if the problem is only asking us for 3, I still didn't do the circle one. They're only asking us for 3, we don't need to do it. So let's say you can write down no table in trusses. No table in trusses. In trusses, what's something else you want to do? You always want to look at the whole structure away, which you've done already in frame problems. Okay, the last piece of trusses is fun.
Are we only gonna look at 2D trusses or?
Only do 2D. Okay, so on today's Tuesday or Wednesday, Thursday? Tuesday. On last Thursday, I gave you the sheet. On one side it says Rule 1 and on the other side it says Rule 2. Pull that out. Does anybody need one? I have a few left. I have very few left, like none. I just have mine. So somebody might have 2 because I had a couple extras up here.
Do you have?
Okay, let's read through this, and I'll underline the good stuff. Let's see. Okay, what we're doing here is we're finding the zero force members. So we know that two force members mean they're connected only on the ends. Three force members means there are three spots that they have forces. A zero force member doesn't mean that it's floating up in air. I don't know why they call it the same thing. A zero force member means it holds zero. There is no load. So we calculated GF to be 750. We calculated CF, is everybody listening? We calculated CF to be 2,500. We calculated GF to be 750. A zero force member is zero. Isn't that really nice? I'd like to find out which one's a zero before I start doing all the math. So that's why we're looking at this. So rule number 1 says, if only two members form a truss joint and there is no external load or support reaction at that joint, the member is zero. So looking at this truss right here, is there a joint where two members come together and there is no external load or support at the joint? Do you see a point? D. This right here, point D, follows that rule. Two members are coming together, there's no external force, and there's no support there. It means that these two guys are zero. Why are they there? Who the hell knows? Maybe somebody had truss members in their garage and they wanted to get rid of them, so they put it there. Or maybe they like things pointy. But basically, that's all you needed was this. Do you see another joint that follows that rule?
A.
A. Joint A follows that rule too. So this is zero, this is zero. There is no reason that somebody needed to design this. That's all we needed was that.
What's the money?
How do you know that A and B, those aren't pins?
Oh, they could be pins or they could be, they are. So let's see. It doesn't say there's no support there. It says there are no reactions to the support there. So if we did the math and figured out, put an AX and AY, well, no, there's no AX and AY because it's transmitted through, right? Remember with trusses, this is a two force member, this is a two force member. The load goes here, load goes here.
So it'd be going towards.
So it's zero. Since those guys are zero, zero. Okay, let's look at rule 2. Rule 2. If three members form a truss joint, which two members are collinear, and the third member, hang on a second. If three members form a truss joint where two of the members are collinear, the third member is a zero force member as long as there are no external forces and supports at the joint. So we have to find a joint where there are three members coming together. Two of them are collinear, one is not, and the one that's not is zero. So, Nick, we're up to you. Do you see a joint where three members come together, two of them are collinear, one's non-collinear? What joint do you see? So we're looking at A.
Yeah. See the joint C.
Joint C.
Yeah.
So at joint C, there are two coming in that are collinear, CD and DB, and one's not collinear. Which one is zero?
AC is zero.
AC is zero. Nicholas, do you see another one? Do you see another joint following this rule 2?
AB.
joint. You're describing,
oh,
it's
joint.
really, this is kind of confusing a little bit, but you are defining a joint. So which joint? You can't say AD, because that's member AD. Which joint?
Joint D.
Joint D has two coming in that are collinear, one non-collinear, and which one's zero?
AD.
AD, and that's what you meant when you said AD. So let's go back to our problem here. Remember that they also wanted you to find CG. So Jack,
It should be 0,
why?
because there's two in here.
Okay, so tell me the joint
Joint
and
G.
tell me which rule.
This would be joint G. which is
Joint
two.
G, rule which one?
2.
2, and which one's 0?
GC.
CG. Wouldn't it be really nice when you look at a truss to figure out which one's a 0 before you start doing all your math? So now, did you have a question on this one?
Yeah.
Okay,
So-
are there any other ones, you guys? Let's see, Maria? So let's look at rule 1. Let's do rule 1 first. Is there a joint where two members come together and there's no external support or load at? Well, I see two places where two come together. One's joint E, but what's going on at E? There's an 1,000, so they're not 0. What about at A? There's a connection, so it can't be. So there's no rule 1. Radian, let's go back to you. Is there a rule 2 where three members, is there a joint where there are three members coming together, two collinear, one non-collinear, no external force or support? Just G. Does anybody see another one? Eric, Enrique?
Isn't there a external force of 2,000 pounds on member CG?
Okay, so let's look, everybody look up here, this is the question I get all the time. If I look at joint G, there is no external support here, no external loads, these two are collinear, this has gotta be 0. I do not look at the 200-pound one, because the 2,000 pound here means that it's transmitted directly through here, and this one, take the 2,000 pound, that middle one doesn't take that.
So it has to be on the joint itself?
You have to look, the rules apply specifically to the joint. Don't let your eyes wander to other joints, stick with that joint.
So what's the purpose of CG then?
It's a stiffener, I mean, there is some load that it's taking, but it's very, very small because there's weights on each of the members, but otherwise we can just remove it. Hang on a second. So radiant, how come B doesn't follow rule 2?
Well, because it has 1,000.
Has the 1,000 pounds. Lucas, how come D doesn't apply?
Also has the
Has the external load.
That just answered my question.
Okay, now, so Eric, we're up to you. Look at this problem up top. Are there any rule 1s?
No.
No. Are there any rule 2s, Enrique?
No.
No. Okay? So take a look at this problem. When you go to solve this problem, it says here, determine the forces in all the members. What are you going to do? Look at the whole structure,
Then break it.
break it. You're going to probably break it here, break it here. You're probably going to wind up doing method of joints because there's not that many members. You're going to look at each joint. So in the end, you're going to need to find A and C. I'd like to send you the solution to the top one for you to look at, okay? So I'll email it to you. Okay, we gotta end. On Thursday, I won't be here. Karen will be here.